Good morning. This is part 2 of lecture 2 of helicopter course. We will concentrate today on helicopter controls. Helicopter is a 6 degrees of freedom body and needs to be controlled in all its axes. On an airplane, the aerodynamic surfaces are attached to the fuselage, so the pilot flies the fuselage. In an helicopter, the aerodynamic surfaces are on the rotor. The pilot will fly the rotor and the fuselage will go along for the ride. The most important component of a helicopter rotor is the swash plate. The swash plate consists mainly in two parts: a non-rotating plate that you see in a figure and a rotating plate. This rotating plate is a control plate which not only slides along the rotor shaft but may move in all directions about its spherical bearing. In a figure you see the pitch links which are connecting the rotating swash plate to the blade, or more exactly to the pitch horns. In this figure you see how the pilot controls go to the swash plate mechanism. You see the helicopter pilot controls, collective, longitudinal, cyclic, and the pedals, and all these going to the non-rotating swash plate and then transmitting the motion to the rotating swash plate. Today, there exist also swash plateless rotors. Example, the K-MAX helicopter with servo flaps. A servo flap is a small airfoil located at about 75% span of the rotor blade, situated on the trailing edge of each rotor blade. These flaps are controlled by the pilot exactly like in fixed-wing airplanes. Moving the servo flap upward increases the rotor pitch and causes the helicopter to dive. We are going to discuss about the pilot controls. The pilot controls are as follows. For the vertical control, we can use the collective stick. This is located on the left-hand side for pilot seated on right side. Sometimes collective stick controls also the RPM of the rotor by a twist grip. Then, the longitudinal and the lateral control is achieved by using the cyclic stick. This is positioned in front of the pilot and can be used to tilt the swash plate. The yawing control is achieved by the pedals. Let's concentrate on each control. First, the collective stick. When the collective stick is applied by the pilot, it will result in the following. For 1 inch collective stick, the non-rotating swash plate will rise. This is connected to the rotating swash plate, which then is connected through the pitch links to the pitch horn. As a result, the blade root geometric pitch will increase at all blade azimuth positions, approximately 3 degrees. The pitch is increasing, the angle of attack is increasing, the lift is increasing, so the thrust force on the whole rotor is increasing. A new equilibrium position is achieved in less than 3 rotor revolutions, and this results in a climb of a helicopter. The cyclic stick is operated with the right hand for piloting control. When one is moving the longitudinal cyclic stick forward, the rotor disc will tilt forward, the thrust force will tilt forward, and the helicopter will pitch down and move forward. Equivalently, for a lateral control, the cyclic stick to the left will result in a helicopter rolling and moving to the left. What happens on the swash plate after giving a cyclic pitch? You see here the helicopter rotor and the different blade azimuths. For a cyclic stick forward, the non-rotating swash plate will tilt forward. The pitch horn is connected to the advancing blade of the helicopter. The advancing blade is actually the blade which is situated at 90 degrees azimuth and is advancing with the rotor. As a result, the pitch angle on the advancing blade will decrease to a minimum. This will result in a decrease in the angle of attack and a decrease in the lift force. Opposite, on the retreating blade, the blade situated at a 270 degrees azimuth angle, which is going back of the helicopter, the pitch of the blades will increase. This will result in an increase in the lift force. As a result, you would think that the rotor disc will tilt laterally. But due to the gyroscopic effects, as we apply a force on the rotor, we will have the response 90 degrees later, and this results in a forward tilt of the rotor. As a result, the helicopter will pitch down and it will move forward. Understanding this mechanism, we can go to the pedals. For the pedals, we are controlling the yaw. For example, if we give a left pedal, the tail rotor pitch will increase. The thrust on the tail rotor will increase, and as a result, the helicopter will yaw to the left. Reviewing. The vertical control is achieved with collective pitch. Directional control is achieved with the tail rotor collective pitch. Longitudinal and lateral control is achieved by cyclic pitch. Rotor speed control is achieved through throttle or automatic rotor speed governor. The range of pilot controls are given in this table. Applying a collective main rotor, 0 to 8 inches pilot control results in a swash plate pitch between 2 to 21 degrees. A cyclic forward afterwards, 4 inches, results in 15 degrees aft and 90 degrees forward of the swash plate. A lateral cyclic 4 inches left-right will result in 8.5 degrees left-right. And for a pedal, 3 inches pedal left-right will result in 6.5 degrees to the left and 22.5 degrees to the right in a counter-rotating helicopter. There are many cross-coupling effects in helicopters. Some of the most important are presented here. First, collective is coupled to the yaw control. Why? Imagine that the pilot is moving the collective lever. In this way, we have a change in the engine torque. This changes the reaction torque. Therefore, one needs to apply more pedal to prevent the helicopter from yawing. Another cross-coupling is the lateral to collective pitch control. Imagine now that we apply a lateral cyclic stick. As a result, the lateral force on the main rotor will increase. Therefore, we need to apply more pedal in order to restore the lateral equilibrium of the forces. Applying pedal results in a yaw unbalance, and this will require again collective stick. Another cross-coupling effect is the longitudinal to the lateral cyclic coupling, or the swash plate mixing. Usually, the longitudinal and lateral control are designed as mixed controls in the swash plate mechanism. Typical control mixing. For 1-inch collective stick pilot input, it results in 1.6 degrees main rotor collective pitch, 1.6 degrees tail rotor collective pitch, 0.46 degrees main rotor longitudinal cyclic, 0.25 degrees lateral cyclic. Often, elevator incidence is linked to pilot collective and forward-afterwards cyclic pitch. Imagine now that we would like to accelerate with the helicopter from hover to forward flight. As a pilot, we will need to do the following. Pull the cyclic stick forward. In this way, the rotor disc will tilt forward. Then we need to apply collective. First raise it in order to keep the altitude and then lower it, because as the helicopter is accelerating, it needs less power. Once we lower the collective, we need to apply right pedal in a counter-rotating helicopter. Right pedal means move the cyclic to the left, and in order to keep the attitude. Concluding, the helicopter is a cross-coupled vehicle with much workload for the pilot. I attached to this lecture 2 movies. A Moran Trying to Hover, showing you how difficult it is to take away with a helicopter if you do not know how to fly, and a video of the V-22 tilt rotor in a pilot-induced oscillation. Both show that helicopters are difficult to fly. I end the present lecture on helicopter controls.